Hello all, good morning from Japan. Our paper today for the symposium title is Minimax Optimum Stochastic Strategy, abbreviated by MOS, for neighbor discovery and selection in mmWave device-to-device networks. Presented by me, Shrif Hashima, postdoctoral researcher at Riken Advanced Intelligence Project, Japan. The co-authors are Professor Koichi Hatano from Kyushu University and involved with Riken AIB, Professor Eiji Takemoto in Kyushu University, Japan, and Dr. Iham Mahmoud Mohammed from Prince Sultan bin Abdulaziz University, Kingdom of Saudi Arabia. Our agenda today, we will have a background on mmWave pros and cons and the challenges that face. Then we will move to mmWave device-to-device relationship and multi-armed bandits in machine learning. Then we will move to the paper motivations, which is diverging in one of the famous multi-armed bandit algorithms to solve a mmWave neighborhood discovery and selection. And afterwards, we will go to system model, which discusses the network, mmWave network structure and mmWave channel formulation and the blockage formulation, and then the mmWave neighborhood discovery and selection problem formulation. Afterwards, we will discuss the proposed energy-aware MOS algorithm that we leverage MOS algorithm to select the best nearby device with considering the remaining batteries of nearby devices. Afterwards, we will have simulation results of proposed algorithm with conventional and random selection approaches in terms of average throughput and energy efficiency and network lifetime. Finally, we conclude our paper. Communication tables to cover the required capacity for users. They leveraged their work to mmWaves that have extra large bandwidths with high data rate transmissions and have a narrow beam width. All of these things have pros of the mmWave, but there are some challenges, which is the high pass loss due to high frequency and short range transmissions due to the high pass loss, and also it is sensitive to blocking. And from this figure, if you see, if this person moved in front of this beam, the transmission will stop on the screen. And also there's a high oxygen absorption and H2O, and it's affected or attenuated by rain and by foggy weather. All of these challenges of mmWave or these characteristics needs to be solved. So it is suitable for short range communications. To solve the narrow beam width of mmWave, there is the concept of beamform training, which we have directional antennas with the main loop is directed to the device under test. But this requires from the base station to perform exhaustive search beamform training, which consumes a lot of time and makes a large overhead and long setup time for the communication linkage connection. So leveraging device-to-device communications is promising because there is a relation between the mmWave and device-to-device because mmWave short range. All of these things makes us to focus on the mmWave device-to-device communications and search on the problem that exists on it. mmWave neighborhood discovery and selection is employed to establish mmWave device-to-device communications. In this process, a device applies a beamform training with all of the surrounding devices to choose the suitable device for constructing device-to-device link. However, beamform training process consumes a lot of time and increases the energy consumption of the devices, and hence it reduces the average throughput of the network. Also, the process of neighbor discovery and selection should be continuously applied to keep on dynamic changes in the environment, like blocking and shadowing. Also, previous work doesn't simulate the real network scenario where the device's remaining battery percentages should be considered. Low battery devices prefer to keep their usage for main calls, primary usage only, not for forwarding data for the sake of other devices, which is the secondary job. Also, direct neighborhood discovery should be applied. Hence, we have to find a continuous method to relax the problem and find the best nearby device quickly without consuming a lot of power. This motivates us for solving future mmWave hurdles by using online learning or self-decision algorithms. This is by making use of machine learning algorithms, especially multi-armed bandits, where multi-armed bandits was used to solve the exploitation dilemma, where an agent continuously tries to explore a new arms, which in our case is new devices, which is exploration, and he have to optimize his choice or his reward based on the current knowledge, which is exploitation part, to maximize his reward. Multi-armed bandit algorithms are divided into two main types, stochastic and adversarial one. Stochastic maps, the reward of each arm is pulled independently from each other, and for adversarial maps, the reward is greatly affected on the nature of the environment, not on the distribution of the rewards. Our main motivation in this paper is to find a good solution for mmWave neighbor discovery and selection problem that consumes more time and expenses large overhead because of the beamformer training process. Hence, we think about leveraging multi-armed bandits for such problem to solve intelligently. So we propose an energy-aware EMOS algorithm that MOS algorithm is adapted for both stochastic and adversarial environment, which is perfect case. And also it considers the battery consumption of the device that simulates the real scenario, and hence it prolongs the network lifetime instead of using all the arms all the time. Network structure will have a macrocell or picocell that serve as a group of devices, mmWave devices. There is a central device that wants to communicate with the best nearby device to have linkage, device-to-device linkage. The traditional approaches are conventional approach and random selection approach. For conventional approach, this device will do beamformer training with all of the surrounding device to select the best nearby one, which is exhaustive search approach. And the random selection approach, this device will randomly select any of these devices to select the best nearby devices. The mmWave channel link equation will be this equation. The received power will be equal to the transmitted power multiplied by the transmitting gain and antenna gain and receiving antenna gain over the line of sight and line of sight of probabilities, which are two Bernoulli random distributions, over the bus loss. This is the equation of the bus loss. P here is line of sight or non-line of sight. Beta B is the bus loss at reference distance 5 meters, and epsilon B is the log normal shadowing. The receiver beamforming gain, dr of phi, will equal to d naught exponential of minus 4 ln 2 of phi minus phi r over phi minus 3 dB square, where dr is the receiver beamforming gain and phi is the angle of the arrival, d naught is the highest antenna gain, and phi 3 minus 3 dB is the half power beam width. Also, we can switch dr by dt to find the transmitter beamforming gain, and theta is the angle of departure. So we will just replace phi and phi r with theta and theta t, and also we will get the equation of transmitting beamforming gain. The millimeter wave blocking will be simulated as spatially distributed cylinders according to the two-dimensional homogeneous Poisson point process, which is probability of line of sight will be delta E minus nabla D. Delta will be E of minus pi omega lambda and the mean of R square, and nabla is equals to omega is a blocked object thinning factor, and lambda is a blocked object blocking density, and E is the mean operator, and R is the blocked object radius. And here we have our simulation regards to the blocked object blocking density. Our problem formulation for millimeter wave device to device nearby discovery and selection will be we will select from all of the devices the device that will have maximum throughput with considering that its remaining battery over the threshold battery. So K maximum is the total number of devices, and eta K is the device link throughput in bit per second at time or round T. And Ek of T is the remaining energy of this nearby device or of this selected device K small at time T, and E threshold is the remaining energy threshold. Our multi-armed banded protocol will consist of at round T we will pull an arm or device K that is associated with a cost, which is the battery consumption due to sending a data through this device. Hence, generally the player of the bandit will be the transmitted or the central device, and the arms will be the nearby devices, and the reward will be the throughput for selecting an arm, and also the budget is the remaining battery level. So this figure is a proposed map protocol for T equal 1 to the time horizon T capital. The algorithm will choose an arm or device K small from group of K capital devices, and the reward will be the throughput, which will be drawn independently distributed from distribution. Then we will reveal this reward, and we are trying to maximize the long-term reward, which will have the best nearby device. In this paper, we will have one of the famous multi-armed band algorithms, which is MOS algorithm, and one of its major advantages is that it's adaptable for both stochastic and adversarial environments. Equation 9 contains the main equation of MOS. For selecting an arm K, we will have, this is the old MOS equation, we will have exploitation part, which is the throughput, and this is the exploration part. This is the exploration part. Then to make this algorithm energy aware, in our case, we added this term dk over ek of t, which reflects the left battery levels of the diffused devices related to their distance from the center device. Equation 8, it's updating of the energy. So the energy of the selected device, the new energy at time t, will equal to the old energy at time t minus 1, minus the energy consumed for transferring or transmitting L data bits to the nearby device. This term or equation 8 is the energy update equation, and also every time the device is selected, the remaining of the battery for this selection process will be reduced. Hence the algorithm inputs will be the threshold level of the battery and the initial energy level of the devices for all the devices, and then we will initialization part we will draw an arm or a device K, and we will get the update of throughput and its remaining energy using equation 8 discussed in the previous slide. And while the remaining energy of the device is over the threshold, it continues on the game or the bandit. We will increase the time and we will apply the proposed EMOS using equation 9, and then we will update the remaining battery, and the game will end when all of the remaining batteries of the devices will be lower than the threshold. The first evaluation metric is throughput, which will equal to the millimeter of bandwidth multiplied by the data transmission time multiplied by the spectral efficiency over the number of neighbors that do beamform training multiplied by the time for beamform training over the plus the time of data transmission. The spectral efficiency, according to Shannon, will be equal to log to 1 plus received power at device K over the noise power, which is zero mean and sigma square variance. The second metric for evaluation is the average energy efficiency, Q. It is defined as the average throughput over energy consumption per selected device in bit per second per joule. Here is the equation of Q. This EK of T plus 1 is initial energy, and EK T equal T capital, which is the time is the final energy. The third evaluation metric is the network lifetime, which is the time spent when the energy of one or more of the nearby devices is reduced below target threshold, which is 0.1 joule averages over the time horizon. These are the simulation parameters utilized in this paper with the references. Our first results curve is average throughput in gigabit per second against the number of devices. Here, EMOS ensures superior performance over conventional and random selection schemes. For conventional schemes under 75 devices, it is reduced than random selection because of the large time consumed for beamform training process of all devices. At 20 and 800 devices, EMOS achieves 1.12 and 2.5 over random and conventional selection is for 20, and for 100 the increment will be 1.51 and 1.89 for conventional and random selection schemes respectively. The second curve is the average throughput in gigabits per second against the blocking density for 60 devices. Here, as the blocking density increases, the throughput is reduced due to the blocked object. Also, the EMOS selection have superior performance over conventional and random selection approaches. The third curve is energy efficiency Q in gigabit per second over millijoule against the number of devices at no blockage. As the number of devices increase, the energy efficiency is increased. Here, the curve shows the superior performance of EMOS over random and conventional schemes with rational increment over conventional and random schemes. Figure 5 discusses the average energy efficiency in gigabit per second per millijoule against the blocking density. As the blocking density is increased, the energy efficiency is reduced. The curve shows the superior performance of EMOS over conventional and random selection schemes. The curve discusses the network lifetime relation against the blocking density for EMOS and conventional and random selection schemes. As the blocking density is increased, the network lifetime is reduced. However, EMOS have greater network lifetime saving due to the added battery term in the EMOS equation. The last curve today is the average reward against the round T, which measures the convergence of EMOS algorithm, and it converges closely to the optimal performance. It's about 98% of the ideal throughput. Our conclusion of this paper, we leveraged MOS to solve the neighbor discovery selection problem in mmWave device communication with considering the remaining battery of selected devices. MOS is adaptable for both stochastic and adversarial environment. Energy aware MOS will not maximize the long-term throughput, but also accelerates the selection process with high convergence rate. EMOS proves its excellent performance over conventional and random selection schemes in terms of average throughput, energy efficiency, and network lifetime. and EMOS easily solves the neighbor discovery and selection problem in mmWave, leading to future promising application. One of the future work includes multiplayer map algorithms for multiple devices doing neighborhood discovery selection simultaneously.